What's up guys, back in with another video. In today's video, I will show you all how my QFT homework looks like, so let's get into it. So here is the homework for the quantum field theory class that I'm currently auditing. As y'all can see, there are 3 questions and there are a lot of symbols. Um, yeah, at first it looks pretty daunting, but it's not that bad, I would say. Um, this first problem, here we have the Lagrangian for a free scalar field. I say it's free. We have this term over here, but this is just a source term, so it's still a free field. We calculate the S matrix in class, and it's asking for us to show that the S matrix is unitary. What unitary means, an operator O is unitary if O multiplied by its complex conjugate equals 1. So all we gotta do is show that this thing, if you multiply, but if you just like change the sign in front of I, multiply it by itself, you get 1. Um, I thought it was actually like that simple, but on further thinking about it, we do have these operators over here. This is the creation operator, this is the annihilation operator, and if we were to let's conjugate this S, that would also conjugate the A conjugate K, which makes things a bit more complicated. So I think I'd have to use the commutation relation between those two operators to show that this does give us 1 if you do that. Anywho, this part over here is probably gonna be a little bit more involved. Calculating probability that this over here. Um, Let me have Feynman diagrams in our homework as well. Um, we showed this one in class. Here's a Feynman diagram for the this should be phi 4. It's kind of strange because you cannot get this from this one over here. But this is probably the phi 4 theory, I believe. Anyways, this is weird. Okay, my professor is a string theorist, so that's a red flag, and the way he explains things are just very strange. And basically, he derives scattering by looking at the Dyson series and then using Wick's theorem for each term in the Dyson series. In my opinion, that's the wrongest way to explain or to derive scattering. How I learned it is that, or how I self learned it is that basically you have to use the Galban-Low theorem and then use LSZ. And LSZ will tell you how to actually calculate the S matrix elements by relating that to the endpoint equation functions, right? However, he derives scattering without even referring to LSZ. So that's the approach that's similar to the one that Schwarzenberg uses in his book No Nonsense QFT, which I don't like very much. Yeah, so this is very weird, pretty much. I'm not used to seeing it written like this. So yeah, his approach to scattering is very idiosyncratic. But anyways, this is still doable. I think he would solve this problem by just using the formula that's given over here. You just check that into the normal ordering right there, and basically the terms that are not already normal ordered go to 0. I think. Um, but yeah, the last problem is probably the easiest one. It's just relativity. It's just algebra, really. We want to express this over here in terms of Lorentz invariant quantities. So that shouldn't be too hard to do, I think. So we have particles colliding head on with each other, which means that the center of mass, which means the net momenta is 0 because they have equal and opposite momenta. So and he wants us to express the center of mass energy multiplied by the three momenta in terms of quantities that are Lorentz invariant. So that means we want to prove, I guess, that this quantity over here is the same regardless of what reference frame you are in. So yeah, that's pretty much the homework. It's due in a couple of days. I should probably do my real homework right now. My waves homework, for waves and optics. It's not as involved as you can see, so I'll probably have more fun doing this homework instead. But yeah, that's what QFT homework looks like. Thanks for watching, and the next video, I don't know. I'll probably make a second channel for these kinds of videos, and just yeah, keep out a look for that. If that's the right saying. All right, adios.